on a wall 12 meters away. Okay. So here it is. Here's the wall. And here's the spotlight. And it is 12 meters away. Okay. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6, okay. So first of all, we have the person right here. I'm sorry. I'm sorry, you can laugh. Sorry about that. That's the best I can do. So he walks in this direction from the spotlight towards the wall. And we are given 1.6, it says at a speed of 1.6 meters per second. And I have to stop and see what this means. So the person started here next to the spotlight and walked towards the wall. So this is the distance covered by the person at any particular instant. So if we call this x, what does this represent?
Minus x.
What does 1.6 meters per second? I walk towards you. I'm a person that I walk towards you, and my speed is 1.6 meters per second. What does this equal to? What does it mean?
Distance.
Is it your velocity?
Yes. How do we write it? Very good. It is my velocity because it's meters per second. Here's my hint. The rate of change of distance with respect to time. So what is it?
Dx over dt.
Thank you very much. Derek, thank you. Good. Moving on. It says, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, so when he is in this position, his shadow on the building is this. I'm going to erase it. That's why I'm using pencil. This one I'm not going to erase, but others I will. So what if he is here now? Look at his shadow on the building now, on the wall. So the shadow is this long. When he is in this position. When he is here, the shadow is this. When he is here, still 2 meters, I forgot to mention that. He's 2 meters tall. So when he's here, look at the shadow on the wall. So it's very clear that the closer he gets to the wall, the shadow is decreasing. The length of the shadow is decreasing. So now I'm going to erase everything else because I only need one. I don't need all this. So at that particular instant, and he is 2 meters tall, I'm going to denote this by y. So the question is, he walks from the spotlight towards the wall. His shadow initially was very tall, and then as he approaches, it will decrease. So I have to make a mental note or a written note, decreases. So I don't forget to have the negative symbol in there. So we are asked what when he is such and such. It said, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? When he's 4 meters from the building. When he's 4 meters from the building, he covered already how many meters? He covered,
8.
yes, 8 meters. When x is 8 meters. But what is the question? What are we asked to find?
The rate of change of his shadow at 8 meters?
Excellent. How do I write it? Perfect. Who said that?
Gabriel.
Yes. How do I write that? So I know exactly what I'm looking for. That's crucial.
I'm not sure what the it was like. It's gonna be like d of something over d of t, but I'm not sure what the one.
We just denoted by y.
Oh, d of y over dt.
That's it. That's it. Very good. Awesome. So obviously I have to find the relationship between x and y. That's all I have. I have 12, I have 2, I have x, sort of, and y. Why do I need to connect x and y? Is because these two are related rates. This is changing as fast, not with the same magnitude, but this changes when this changes. So the change in y is triggered by a change in x. So then dx over dt and dy over dt are related. This happens, this changes because this changes. So the rate here triggers the rate there. That's why we call these related rates of change. Maybe that would be better if we said related rates of change, but that's what we mean. Okay, so we are going to, so that was page 7. I think I didn't write anything here. Yeah, I didn't. Okay, page 9. So I'm going to copy that drawing, but exactly what we need to copy. Does this trigger any memory? What I just graphed?
Aren't they similar triangles?
Great job, Derek. Thank you. Similar triangles. So this tiny triangle is similar to this triangle. First, I have to convince you of that. I haven't convinced you of that. In order to show similar triangles, I have to show just 2 pairs of congruent or equal angles. Yeah, of course, no problem. So this is a pair. This is the same with that. And here's the other pair, because this angle is present in both. Obviously, these two must be the same. Because I showed at least 2 pairs of congruent or equal angles, then I can write proportions with the sides. But writing proportions with the sides has to be done in a particular order. All sides at the top have to come from one particular triangle only. All sides at the bottom have to come from the other triangle only. And even those have to be in a particular order. Let's suppose I start with a common angle. So this is a common angle. If I start with a common angle, the opposite side in the small triangle equals what? Anyone? Anyone who hasn't said anything yet today? Trey?
90 minus the angle that you get.
Say it again, Oscar.
90 minus the angle that you get.
So we are talking now about the sides of the triangles. We already shown that the triangles, the two triangles, the small one and the big one, they are similar because they have all angles are congruent. But now we want to write proportions with their sides. We start with a common angle. What is the opposite side of the common angle in the small triangle equal to?
2.
Thank you. What is the opposite side of the common angle in the big triangle equal to?
Y.
Thank you. I'm moving on to this, but I don't have any information. So I could write this over this, but it's not going to give me anything. I don't have any information about those two. So I'm moving on to the last angle. What is the opposite side of this angle in the small triangle equal to?
X.
What is the opposite side, because these are congruent, what is the opposite side of this angle in the big triangle equal to?
12.
That's it. So all we needed was 2 over y equals x over 12. What do we need to do next? Common sense, algebra tells us to do what?
Cross.
Very good. So xy equals 24. Remember, this equation has two functions of time. What is our next step?
Find the derivative with respect to time.
Excellent. I'm ready. One note before you tell me what to write. Notice that this piece never comes into play till we are completely done. Completely done. The function is determined, the derivative is determined, and now I'm ready to plug in numbers. Okay, the same thing here. This piece has nothing to do with anything till the last moment when we are ready to plug in numbers. Do not involve it in any shape or form. Okay, ready? Anyone?
So we're going to use the product rule on XY.
Yay! Ready.
So, let's see, 1. So the derivative of x. Yep.
Times?
The derivative of y.
Is that how we differentiate a product?
This is y.
Plus?
X times the derivative of y.
Not the derivative of y, be careful. dy over dt equals? How much?
20.
0.
Thank you.
0.
That's okay. Thank you. Okay, so what are we after again?
dy over dt.
Great job. So this goes to the other side and I divide by x. So dy over dt equals negative y dx over dt, everything divided by x. Only now I'll say when x equals 8. This is given to us as 1.6. This is given to us as 8. But that's not a problem, because if I know that x is 8, what could y equal to?
3.
Very good, awesome. And it's done. So it's negative 3 times 1.6 divided by 8, whatever that equals to. Negative 0.6. Measurement unit, please. Yeah, this is 3.4.8, of course. Measurement unit, please.
Meters per second.
Very good. So this means that when the person is 8 meters away from the spotlight, right here, let's say, or here, doesn't matter. I don't know where, it doesn't matter where. So let's say this point is 8 meters away. The shadow, his shadow on the building, on the wall, is decreasing at that instant by 0.6, decreasing by 0.6 meters per second. And those two rates are related. How are they related? When one is 1.6, the other one is negative 0.6. That's the relationship between those two. And the relationship between those two is this one. Give me any x, I'll determine y, and this is constant, and I can determine that. So this is the equation that relates them, the variables, including the rates, their rates. Okay, let's look at 2 cars this time. So 2 cars start moving from the same point. Sorry, one travels south at 60 miles per hour, the other one travels west at 25. At what rate is the distance between the cars increasing 2 hours later? We're gonna read it again. Let's draw a picture first. So they start at the same point, and one travels south at 60 miles per hour, and the other one travels west at 25 miles per hour. At what rate is the distance between the cars increasing 2 hours later? I'm going to call this W. Of course, this is on the x-axis. I'm going to call it X. This is on the y-axis. I'm going to call it Y. And what are we asked? And at what point? So 2 cars start moving from the same point. One travels south, one travels west. This one at 60 miles per hour. This one is at 25 miles per hour. And we're asked to find, again, at what rate is the distance between the 2 cars increasing 2 hours later?
W over T.